magnetic field going this way and the velocity is somewhere this way. So this, let's say this is 90 degree. It's a 3-dimensional thing. And let's say I have an electric field like this. So this is a 3-dimensional thing, something like X, Y, Z. Okay. So now I want you to think what will happen. So you see V and B are 90 degree, right? So B cross B. So look at this. B is this way, right? Curling fingers. So start with B cross B, which means start with B and then go to B. So look at my thumb. This going into the board. So it's something like, it's going to go like this, opposite of this. Do you agree? Force is going to be in the direction of the thumb, right? B cross B. So I am going to say this is based on the value of QV cross B, or I can say QVB sin theta. But sin theta is, what is theta here? 90 degree, which means it becomes 1. So QVB sin 90. Okay. Folks, if you are not able to read it, maybe I will make it bigger. So I am going to say Fm is equal to QV cross B is equal to QVB sin theta. So we say QVB because sin 90 degree is 1. Any issues, anybody? Aditya, are you finding it difficult to read it or what? Then why don't you come here? I have a lot of space. Come this way, I think there is, I don't know if you have enough here. So I am saying this is my force direction, right? But if the velocity is going this way, right? Which way is electric field is going to, so that is electric field also, right? Until now what we saw was only magnetic field, right? We didn't talk about electric field in the previous 3 cases. So now we are given a situation where you have magnetic field and electric field. Okay. So magnetic field is nothing but you keep a north magnet here, south magnet here, that's what we call as magnetic field. You keep a plus plate here and minus plate here, that is your electric field, right? So don't think it's very complicated system or anything. Just like what I showed you. If you make a magnet, if you keep a magnet, that's your magnetic field, right? So this is magnetic field, this is electric field. So in the electric field, I said this is plus, this is minus. So if you put a plus charge here, which way it's going to go? Which way is the force? It's going to go towards the minus. So it's going to go towards the electric field direction. Do you agree? So that means Fe will be in the direction of this way. So you say Fe is this way. Fm is this way, Fe is this way. So Fm is given by QVB, right? Fe is QE. You already know this. Agreed? So the force on the Fe can be adjusted by adjusting the electric field. The force due to magnetic field can be adjusted by adjusting the magnetic field. Can you see that? Right? So if I change this, I will change this. If I change this, I will change this. The charge Q is same and the velocity I am not going to change. Right? So that means I can control. So meaning what I am trying to say here is these two are control parameters. I can control it. If I want stronger electric field, I can increase the electric field. If I want stronger magnetic field, I can increase the magnetic field. Right? A very strong magnetic field, I am sure you have seen somewhere. So have you seen any strong magnetic field somewhere? Have you experienced it anywhere? No? That is, you are talking about the magnetic trains, magnetic levitation. Okay, very good. So that is very strong magnets. Train. Normal Indian trains, where do you have magnet? In two carriages, where do you have magnet? Okay, in between that, okay, you're talking about this one. That this thing, right? I don't know if that is magnet. Cranes, yeah, cranes use magnetism. Magnetic field experienced by sky. Okay. No, Earth's magnetic field. What is compass? Compass is a device. Magnetic compass. You're talking about this one, right? Right. But that operates based on magnetism, right? If there is a magnetic field, it will show you some direction, right? But one more good example is your clocks. Clocks. Okay, some natural magnets you are talking about. Okay. Anything else? I'm sure. Have you seen some magnetism somewhere in your hospitals? MRI, very good. Magnetic resonance imaging, right? So MRI scan, CT scan, all these things are. So you see this big tube which you are seeing, right? The patient will be like lying here, right? So it will be going in. So this is nothing but big coils, electric coils. And when you pass a lot of current here, you will be producing very high magnetic fields. So that is what is MRI, magnetic resonance imaging. So if you want to study some heart or brain, generally MRI scan is taken. Okay. For bones it is generally X-rays, right? But for heart and brain it is mainly MRI. Okay. So this is called Helmholtz coil. We'll talk about this later. So it's a very strong magnetic field, right? In fact, there are a lot of accidents where if you enter into the room with having some kind of ferrous material, then you are in a big trouble. You can even get killed. Right? So they will make sure that you are not wearing any kind of iron or any kind of steel substances. Right? So it's a very, very powerful magnetic field. Even recently, like 2-3 months back, there was a big accident in some Mumbai hospital. So without switching off this magnetic field, right? So somebody just took a oxygen cylinder. Oxygen cylinder, it is steel, right? So it was just attracted directly, and that guy got killed. Because the moment you enter into the room, it will be just pulling you so much of force, so you don't have, very high magnetic field. So in the order of say few Teslas, so it will be very, very high. Okay. So in fact, in Anna University, there is a separate course called Medical Physics, MSc Medical Physics. So after studying your BSc, you can, if you are interested in these stuff, you can go into that field. Because a lot of hospitals, they use a lot of these kind of radiology, X-rays, all these things are coming under medical physics. So you have to study these things. Okay, so let's get back to the theory here. The reason I'm talking about all those things is you are experiencing magnetic field, electric field, all these things on a regular day-to-day basis, right? So particularly magnetic field, if not electric field. So let's see. So I said these two are control parameters. I can control it. Control parameter. So suppose if I say that I'm adjusting the values such that this is equal to this, right? So imagine a situation that I'm adjusting the B and E value such that adjust B and E values such that Fm is equal to Fe. you can remove this magnitude. So let's look into the magnitude, because it's already equal and opposite if I say it is equal. So Fm is QVB, Fe is QE, right? Remember, these things are subscripts, right? Subscript means you have to write it a little bit small, right? Very often I see people writing like this, right? Is this subscript? This is ion symbol, right? Fe, right? So many people do this kind of mistakes. So you don't know the difference between subscript and, so you should be writing like this. Okay, so what can I cancel? Can cancel Q. So the velocity V is given by E by B. Okay. Any idea what this means? If this force is equal to this force, what is the net force acting on the charge? 0, right? So if that is the case, the charge will go straight, undeflected. Are you following what I'm saying, right? So that means if when Fm is equal to Fe, net force on charge is 0. So the charge will fly through undeflected. Okay. And this concept is used in an equipment called velocity selector. Okay. So this principle is used in, let us call it as used in the equipment called velocity selector. So what it means is, as the name suggests, it says velocity selector. Any idea what that means? Any guess? Selector. Selects the velocity. Okay. I think little more than that. Sometimes when the charged particles are coming out, right? So let's say it's just flying out like this. So the charged particles are coming out. All of them will not be having the same velocity. But let's say if I want to do an experiment with particular velocity, let's say I want a velocity of 5 meters per second or say 10 meters per second, right? So one will be say 5 meters per second, the next one would be say 6 meters per second, the next one would be 7 meters per second. Maybe here it's again 6 meters per second. So something is 10 meters per second. So it's a mixture of different velocities, right? So let's say charged particle is coming at different velocities. If I had a setup like this, what I can do is I can adjust the E and D such that I want, if I want to get say 7 meters per second, right? I adjust the E by B such that the B is equal to 7. So if that's the case, what will happen is this 7 alone will be coming out straight and deflected. And all the others, right, only for this particular E by B, right, you will be getting a value of 7, right? So in that case, all the other velocities are going to, it will not be equal to this situation. The force experienced by the other charged particle will not be equal to this case, Fm is equal to Fe. Okay. So in that case, what will happen is these velocities will be experiencing some forces. So it will get deflected. So these things are deflected. And only charged particle which is coming at this particular velocity which you want, right? So again, I am giving you some numbers just for your understanding. If you write the numbers in the exam, it's confusing for the examiner. So let's say required velocity. required velocity v is equal to E by V. So this kind of setup is called velocity selector. Because what I'm trying to say here is only in this particular case Fm is equal to Fe. In all the other cases, maybe the Fm is more than the Fe. Are you able to follow what I'm saying? Because the Fm is depending upon the velocity, right? Are you following what I'm saying? So let's say in this particular case, Fm is equal to Fe. What about 6? If I put 6 here, it's not going to be equal to that same value of Fe, which means it's going to be bigger or smaller, which means either it will be deflected this way or it will be deflected this way because of the force experienced by it. Which means if I have the equipment like this, whatever is coming out of the equipment, I will get only the required velocity. Okay, so this kind of setup is used for a lot of nuclear reactions and these kind of things, experiments, physics experiments. So they can choose what velocity it is coming and hitting some other particle. Right? So this entire thing is velocity selector. Okay. So I hope you are able to follow up to this, right? No issues. So maybe you may have some trouble understanding this, but basically it's just nothing but only one particular velocity will be equalized, right? Fm is equal to Fe. All the other velocities will not be equalized, which means those things will be experiencing some force. If they experience a force, it will be deflected from the straight line path. Following what I'm saying? I don't see much of a bright face, but at least up to this, sorry folks, okay? Okay, so take down this. Some of the things, if you don't understand now, don't worry. As days pass by, probably it will make sense as you keep studying.